Yeah, I haven't said anything yet. I think I'm unmuted now, or one of me is unmuted. There's two of me here. Okay. So I assume everyone is looking forward to their midterm marks. The assignment had some errors in the answer key. Please recheck. Those have been corrected. They just got uploaded wrong. They were right in our answer key, and just when they got inputted into the online system, it just went wrong. And I'm sorry for that, because some of you got the answer right, and then you got told the answer was wrong. You also should be able to now see what the correct answer is and all that. That was an error. That was entirely an error on my part. I just didn't check the right checkbox in the right sub thing of checkboxes. Hopefully that is working now, and you can actually see what the correct answer is and what you answered. So that might help. Okay, so what I want to do today is I want to talk about comparing Sn2 and Sn1 reactions, but floor is open to any questions first. Do that when we has questions. Okay, let's so if you've seen the lectures on Sn2 and Sn1, there's, hopefully you have, there's sort of things which favor Sn2, there are things that favor Sn1, and we need to worry about edge cases, as always. I promise not to screw you with edge cases on the exam, and if I do, it'll be I won't be screwing you. I'll be putting one in and I'll say justify your choice. And maybe both will be acceptable. You would just need to explain why one, why the other, and why you think the balance is going this way or that way. So we'll do an example of that today. But let's start with example here. Yeah. Chitra, can we go over examples of ranking stability for Sn1 and Sn2? And how resonance plays a factor? Yeah, we will definitely do these. Okay. So let's take a look at this. The questions, so let's say the question is, draw the product of the following substitution reaction. Define and show the mechanism of that. So what I'm asking you with that question is a couple of things. I'm asking you to draw the product, show the mechanism, but I'm also asking you what is the mechanism? Is this Sn2 or Sn1? I've told you it's substitution. I'm going to actually have to look through what my old notes said on that, because I'm sure what I said was intrinsically sensible and brilliant. In the meantime, while I'm looking up my slides on the question that Alyssa just asked, if you want to try this and try and determine if it's Sn1 or Sn2, try and draw the mechanism and try to draw the product. It is this, and I'm telling you it's a substitution reaction. And now I'm going to go digging into my scary set of files. Well, good, I actually found it. It did not take long. Yeah, we're definitely going to do Sn2 stereochemistry. Okay. So anyone have an idea of whether this is Sn1 or Sn2? And if so, why? The coffee cup is empty. Perfect. I love all these answers. So one thing to think about isn't so much SN2 is you do SN2 because of something. It's more you don't do SN1. We're always competing with reactions. SN2 chugs away at a steady rate. SN1 really depends on the stability of the cation. Would be, if this left, this would be a primary carbocation. Can't get primary carbocations. They're not a thing. So it has to be SN2 because we can't make the carbocation. Yeah, well, if it's a substitution reaction, well, it's we can eliminate one of them. What we're doing is we're trying to eliminate reactions, and what's left is what it's got to be. And so if we can eliminate the SN1, that leaves us with only the SN2. So yeah, it's an SN2. So for the SN2 arrows, the bond between the oxygen and the carbon forms as the bond between the carbon. I'm drawing with my hands, and my hands aren't good. As the bond between the oxygen and the carbon forms, the bond between the carbon and the iodine breaks, and they're simultaneous. There's no intermediate. Perfect. Okay, let's try a different one. Okay, so this one, are we thinking it's SN1 or SN2? No opinions. Any opinions? Okay, let's think about the stability. So what you should, right, so think about the stability of the cation, what you can make. Tertiaries, like going SN1. Is this more stable than a tertiary? Is this cation more stable than a tertiary cation? Yes, it is. It's resonance stable secondary cation, right? Because if it left, it would be that would have a resonance structure. So that tells us one thing. Now that doesn't answer it. Just because can that starting material react through an SN2 mechanism? Yes. But we also have to consider what the nucleophile is. A good nucleophile is really reactive. It wants to react. It would help drive that. SN2 needs a strong nucleophile, right? Because the nucleophile matters in SN2 reaction. You need a good nucleophile. In an SN1 reaction, any 50-pound weakling can be a good nucleophile because the nucleophile does not matter because you made a carbocation. So anything with electrons is good enough. Again, all my analogies I'm coming up with in my head are completely obscene and I cannot share them. And I recommend that you develop your own analogies. So the methanol is protonated. It's not O- like the previous example. So it's neutral, so it's not a super strong nucleophile. It's not really interested in doing anything. And so you need some encouragement. So when the leaving group leaves, now suddenly it can act as a nucleophile. So the nucleophile has no great desire to do anything, and strong nucleophiles favor SN2s. We have a stable carbocation, we have a weak nucleophile, we're looking at favoring SN1. Note that it doesn't matter which of those two carbons, which of those two resonance structures I attack, they're absolutely equivalent because the molecule is symmetrical. And note that we started with stereochemistry in the starting material. We have lost our stereochemistry because there's no reason we should attack the bottom face or the top face of that carbocation any more than the other one. There's nothing else on the molecule. There's nothing preferring attack from one face or the other. Okay. There's no tertiary carbon there, Jesse, just to be good. And methanol, yeah, we release the proton. We're going to generate an equivalent of H+. We have a Cl-. So frankly, we've got some HCl being formed. So SN1 is more, as it says in the notes, is more common in neutral or acidic. No, you would not lose marks for not including the HCl. I don't give a shit about the HCl. You can include it if you like. How do you know when you've lost the stereochemistry? You did in SN1. So let's do another example. I'll make it so it'd be an example I managed to give. It'd probably be the sodium salt, actually. Okay. So, yeah, the methanol acts as a polar solvent. And polar solvents also favor SN1s, polar protic solvents. So let's do this example. What do we think we have? Jesse is in for the SN2. We've got agreement from Faith, so we're 2-0, which was a score aligned into injury time last night. That was a great game, by the way. Okay, so we're 3-0. Okay, so SN2, I agree, it's SN2. What is your basis for that, Jesse? What's your analysis that you did? What did you think about here? Strong nucleophile, right. We've got a negative charge. We're under basic conditions. Our nucleophile has a drive to not be basic. We've got a good leaving group. So this is SN2. Why? Strong nucleophile. Favors SN2. Good leaving group. Does a good leaving group favor Sn2 or Sn1? Does it favor either one particularly? Yeah, it's a wash. So looking at the quality of the leaving group, basically can say, hey, I think I'm going to get a fast or a slow substitution, but it doesn't really tell you if it's going to be Sn1 or Sn2. Like an iodide is a better leaving group than a chlorine because I minus stabilizes a charge better than a Cl minus, but it doesn't tell you if it's Sn2 or Sn1. Generally, Sn1s really struggle with really bad leaving groups, but Sn2s struggle if you have a bad leaving group, not a good enough nucleophile. I guess the Sn1 has no way to compensate for a bad leaving group. The Sn2 you can have a stronger nucleophile. But good leaving group, it doesn't really favor both. It's a secondary carbon, no resonance. This is the borderlands between Sn1 and Sn2. Primaries, always Sn2. Tertiaries, always Sn1. Resonance stabilized carbocations, except for the allyl one. Except for the allyl in this exact molecule. You can change the leaving group, but those 3 carbons. Every other resonance stabilized carbocation tends to favor Sn1. So secondary no resonance can go either way. So we need to look at the other components. And we have an aprotic solvent. And an aprotic solvent does not stabilize a nucleophile because, again, when you have a minus charge on your nucleophile and you have a protic solvent, then you can make hydrogen bonds with it, and it decreases the nucleophilicity of your nucleophile, weakens it. Aprotic solvents don't do that. There's no hydrogen bonding with the solvent, and so S minus is S minus. It is nucleophilic. It wants some juicy electrophile. And also, because your solvent is aprotic, you can't make those strong interactions you can make with a protic solvent with the carbocation. You can't stabilize the carbocation as well. So aprotic solvents disfavor Sn1 reactions. Yeah, okay. Let's go over what aprotic and protic is. So a protic solvent, H attached to heteroatom. So something like water. Water's got H's attached to oxygen. Methanol. It's got an H attached to an oxygen. Ammonia. You can use it as a solvent. You have to run your reactions cold to make liquid ammonia, but H is attached to a nitrogen. You can do reactions in neat hydrogen fluoride. I do not recommend it. I've done it once. It was the scariest fucking thing I've ever done in my life. But it's a protic solvent. You can run reactions in acetic acid. It's a protic solvent. You have an H attached to a heteroatom. You can, if you really like stinky things, you can run reactions in ethane thiol. I wouldn't. It's horrible and disgusting. But it's a protic solvent. You have an H attached to a heteroatom. Aprotic solvents. No H attached to heteroatom. because they're the opposite of protic. They are aprotic. Now, normally we're talking about polar aprotic because you have non-polar aprotic. Hexane is a non-polar aprotic solvent. It's really boring, but you have polar aprotic ones. THF is one of them. This is what's here. There's an oxygen, which gives us polarity, but there's no hydrogen attached to it. You get things like DMSO. Or DMF. Or if you're on the weak end of this, like something like dichloromethane, which I do abbreviate as DCM, and I never should. I should always write CH2Cl2, but habits die hard. Also called methylene chloride, because why not have 3 names for something? So in none of these cases do we have a proton attached to a heteroatom. Why is that important? Polar aprotic solvents can't H bond. Now, it's not H bonding itself that's normally particularly super important. It's the fact that H bonding is a really, really strong dipole, and they don't have super strong dipoles. DMSO is a little bit of an oddity. It's got a really strong dipole, but it doesn't H bond, and so it doesn't do some of the things. DMSO is weird. It's kind of in between, but for this course, we're going to treat it as a polar aprotic solvent. In reality, it can do a little bit of both. Whereas protic solvents, you have a really strong hydrogen bond. That hydrogen is drifting off, right? Like in water, the hydrogen is always coming on and off water. It's just really promiscuous. Whereas in THF, the hydrogens are not coming off the carbons. Can I explain why aprotic solvents aren't necessarily going to be polar, Amanda? You can't have non-polar aprotic solvents. Like as I said, hexane is an aprotic solvent. All the ones I've drawn here, though, have a dipole moment. One side of the molecule is more polar than the other side. Like the charge is more negative than the other side. So like THF, the dipole lies towards the oxygen. DMSO definitely lies towards the oxygen. On DMF, it's kind of in between the nitrogen and the oxygen. And on dichloromethane, you can't see it that way when you don't draw it as a tetrahedron. But let's see, you have chlorine, hydrogen, hydrogen. The dipole lies towards the chlorines. Like splitting them, right? Bisecting the 2 chlorines. So all of these things, why are we only considering the polar ones? Because mostly anything we'd be interested in doing, like if you took sodium thiophenol, which is what we've got up here, and you try to put that in hexane, it would precipitate out. It wouldn't be soluble in hexane because it's really, really polar, and like dissolves like, right? And so you can't dissolve really polar things in really, really non-polar things. So if we're using a really non-polar aprotic solvent, nothing's going to dissolve in it. To actually get an SN2 to go, you want to use the least polar aprotic solvent you can that can dissolve everything. Because the more polar your solvent, the better it stabilizes everything. And we don't want to stabilize stuff to get an SN2 to go. We want that sodium thiophenol to be as unhappy as physically possible. We want it to be stressed and upset and angry, because if it's all those things, it's going to react. If it's perfectly comfortable, if it's surrounded by lovely soft pillow charges, which are stabilizing its negative charge and making it feel comfortable, it's not going to react. So we want it pissed off, and so we want it to be as non-polar as possible, because that's going to piss it off, but still be polar enough to dissolve it. Yeah. So there's nothing special about polar aprotic solvents. It's just that they're too non-polar, you can't dissolve anything. But yeah, no, I agree. It's kind of confusing. It's like, what's so special about this? That's the answer. Okay. So when we're looking at the factors here and we're considering all these things, everything's pointing towards the SN2. The only things that are kind of saving the Sn1 is it's a secondary carbocation, but you know that can go either way. And the leaving group's pretty good, and that can go either way. So we've got, what really drives us though is we're under basic conditions. It is impossible to get an Sn1 to go under basic conditions. Because if you're under basic conditions, you're not going to make carbocations. Why? It's not because like there's some magic instability of carbocations in basic conditions and like the carbon senses the pH is below 7 and it's not going to, or above 7, it's not going to react. It's more because if you're under basic conditions, the Sn2 becomes fast. The reactions become fast. And so they outcompete the formation of the carbocation. You never get a chance to form the carbocation before the Sn2 can occur. Everything here is about speed and speed differences. We're trying to speed up or slow down one or the other mechanism by changing the conditions. So this is going to be an Sn2. So it attacks, and the leaving group leaves at the same time. So in the previous example, we had done an Sn1, and we said, look, you lost all your stereochemical information because you went through a carbocation. Carbocations are flat. Nothing interesting happens to a carbocation. Do we lose our stereochemical information here? Yeah, no. Like it transfers. So there was information. Our nucleophile relies on coming in opposite our electrophile. It has to. It's all about that antibonding orbital we were talking about last class and in the lectures. It has to come in opposite. So if the iodine was up, the nucleophile is coming in from the bottom. Perfect. Great job, Jesse. Exactly. All you guys are, you got it. Literally, that you've got it. Okay, let's take a look at another example. I'm going to do one right now. This is actually a little bit of a question to think about. We can do one where the stereochemistry is not. I can try Alyssa for an Sn2. Yeah, because you know what I'm doing here. Yes, and I'm trying to think of an example where it's not as obvious because it is normally actually pretty obvious. We'll throw in a trick question in a moment, though. I promise. Anyways, this one. What do we think and why do we think it? So what is the mechanism? What is the product? Got Jesse in with the Sn1. I is leaving group. Yep. So if we do that, we make a carbocation. It's a secondary carbocation that's in that middle ground. Doesn't necessarily, it doesn't, at this point, we've looked at the carbocation. We haven't eliminated either Sn1 or Sn2. We haven't really favored either one either massively. I would note there's a couple of things I want to draw your attention to over what I think about with the structure of this. Remember that for the SN2, your nucleophile needs to come in opposite your leaving group, right? Is there anything here about the structure of the molecule which would make that a little bit more challenging? Yeah, so, right, you have the isopropyl group sitting above, right? Like this isn't the same molecule, of course, but if we have here, so we got a carbon here with an iodine on it. There, we got this carbon with an iodine, and next to it we have another carbon that has this thingy up here. And this isn't as big as an isopropyl group. I made it small, but our nucleophile is going to need to come in opposite the iodine. This is kind of in a way, it's stopping us coming in from this angle. I'm banging into it. So I need to kind of come in more from this angle. So I've reduced the modes of entry I have. And so I'm slowing down the SN2 by having a group next to this. Is that a huge factor? No. Isopropyl is big, but not ridiculous. And there's only one of them. And so the other half of the molecule is kind of available. But it's still something to think about. Everything is something to think about. And it should go into your calculation. So secondary carbocation. Isopropyl interferes, partially interferes with top face. Somebody pointed out protic methyl group. That was Alyssa. So we've got, I assume what you mean is you have a protic methanol thing. Protic solvent. So we're polar protic solvent. Are we under basic or acidic conditions or neutral conditions? Yeah, a neutral, right? There's no acid here. We are actually going to generate some HI as the reaction goes on. So we're going to shift from neutral to acidic. So that's why neutral and acidic are more or less equivalent. Whenever you do reactions, SN1 or SN2s, and you have like an iodide leaving group, you're almost always going to generate acid. And so even if it's starting neutral, it's going to shift acidic. It's only when you're basic that you're basic. So that's why we kind of gather basic and neutral and acidic kind of get gathered together because neutral will become acidic. And so it's going to be an SN1 reaction. Now in an SN1 reaction, the carbocation is flat, right? Do we have a preference for the top or the bottom face of this carbocation in this case? I'll accept acidic too, Jesse. It's going to go acidic. You're going to make each up. There's no real difference. Yeah, we're going to prefer the bottom because the isopropyl group is slightly blocking the top. So it's an SN1, but the major product is going to be from the bottom. And if you balance your equation, you'll get some HI. If I had asked you to indicate the major and minor products, then you would need to answer it like this. You don't need to write the HI. I'm just noting that so you can sort of see that, hey, the H came off the methanol, the iodine came off the molecule, they gather together. Oh, look, it's acid. So neutral drives towards acid normally under these conditions. Okay, let's do something with a funky Okay, so we're increasing the complexity a little bit here because we're staggering a couple of things we need to think about. So we haven't discussed this in a lot of detail right now, but sodium hydride is never a base or never a nucleophile. There was a paper that was published about it's probably close to 10 years back where somebody said, oh, look, we use sodium hydride as a base, as a nucleophile, and it got all this news because it was being used as a reducing agent, because if H minus is a nucleophile, it's a reducing agent, right? Turns out it wasn't. Like, there was like other stuff going on with their reaction. It wasn't true. Sodium hydride just doesn't act as a nucleophile, and you can ask why, and I have to say I don't know. It's a base, and I don't know why it's not a nucleophile. I don't see why it shouldn't be a nucleophile. It's probably got something to do with the nature of the sodium hydrogen bond, and I clearly don't understand things very well. Yes. Claire. No, the H doesn't leave the methanol. The methanol acts as, there's nothing to get the H away. So Drake asked, does the H leave the methanol? No. The methanol reacts. Sorry, I didn't draw. I should have drawn this in. I'm very, very sorry. You're absolutely right. Just skip to the product. The H is on the oxygen when it's attached. So you make the oxygen carbon bond first, then you take the H off. I'm going to use the I minus to do that, but you could have used another equivalent of methanol. That would have been fine. And that takes us to the products. Yes. Faith and Jesse nailed it. So it's going to make the ring with the sulfur as nucleophile. So again, we're talking about Sn1, Sn2 reactions. The fastest reactions are acid-base reactions. Just get like that freaking tattooed. Like, what's the most stable carbocation and the fastest reactions are acid-base reactions? Like mantras kind of thing. Write them on the top of your exam. I don't give a shit. But it might be helpful because that comes in. So you should always think about, hey, wait a second, before I get too caught up and get too excited, is there a simple acid-base reaction I can do? Yeah, there's a simple acid-base reaction you can do. And so hopefully somebody can tell me what that is. Well, there's no HCl for the sodium hydride to react with. So sodium hydride is definitely the most reactive thing here because it's H minus. Yes, there we go. Thank you, Samantha. Yes, Mackenzie, I can. So we're going to take off the hydrogen from the sulfur. Is the most acidic proton on this molecule. If we do that, we get that. Yeah, and then your sulfur can act as a nucleophile. You have a leaving group. They're in the same molecule. You count your ring size. That's going to make, and you can actually just, when they're marking the midterm, somebody pointed out that someone, did this and they numbered their atoms. I think they're transferring something to a Newman projection, and they numbered their atoms, and then they numbered the atoms of the Newman projection, and then they stuck things on the wrong atoms. So you don't get any marks for numbering. I don't care about it unless you're naming things, right? I don't care about the numbering. Numbering is a tool for you to make sure stuff is connected to the right stuff. So we're hoping it was just a brain fart because stupid mistakes happen when you write chemistry exams. Okay. So it's a 6-membered ring. It's 5 or 6. That's great. That's what we want. I would just start by drawing your 6-membered ring. Now this is where those tricky things is, what's the stereochemistry doing? So what you're going to need to do is think very, very carefully about what this means. Because suddenly we bent and rotated things and everything's a little bit weird, right? So we had the chloride coming out of the plane, but now I have the sulfur in the plane, but it's got to be opposite to where the chloride was, right? So there's a couple of ways you can address this. Yeah, you're going to be. I'll get there, Amanda. That's good. So Faith is asking the good question. Is it coming behind, push the methyl up? Yes, but let's just make sure we're doing this stepwise so that we're not skipping things, because it's very easy to fuck this up. What I would do is I would draw the product the way I want to. So I'm going to want to have this sulfur carbon bond like that. Then what I'm going to try and do is let's draw the chlorine so it is directly opposite that. So that's carbon 2, that's carbon 1. So just let's keep track of where everything is. So I've dropped the chlorine into the plane. So like sort of I'm thinking about the S minus is coming in directly opposite the chlorine. Then what's going to happen, right, is I'm going to push the chlorine away. The methyl group is going to stay up. The hydrogen is going to stay down. So the methyl group there is going to be up. We have to be very careful when we're unfolding, because it's really easy to sort of say, oh yeah, the sulfur comes in from the back, then the sulfur is going to be down, but we don't draw it like that. We draw that as the ring. We draw them all in the same plane. So we have to draw the substituents off. The other thing you can do is you can assign R and S to carbon 1, and you know that you're going to flip the chlorine for sulfur. So all you need to do is draw, if it was R, you need to draw the S one. The one caveat I'm going to say you have to be cautious about is when you're doing Sn2 reactions, not all S's become R's and R's become S's, because sometimes priorities change. Maybe the leaving group was your #1 priority, but your nucleophile isn't. We'll do an example of that. I'll show an example of what I mean. So you need to be a little careful if you're running entirely off of R's and S's, because theoretically, if you do an inversion of configuration, you switch the R to an S. Okay. I want to talk about Amanda's question. I'm going to flip back so that Mackenzie can take a look at what we needed, and I'll talk about Amanda's question. What do we need when we're determining if a ring should form? So we're now going to do an example. I'm throwing away the punchline where we're not going to get a ring. You get rings when you can make 5-membered rings or 6-membered rings. We also saw a lot when we did the alkene chemistry. We made a lot of 3-membered rings with like heteroatoms when adding double bonds, and that was okay too. But you don't normally see a lot of 4-membered rings, and you don't see a lot of 8 or 9-membered rings. You tend to do reactions between molecules rather than within molecules in those cases. So you will make rings if you can make a 5 or a 6-membered ring. So let's do another example. Okay. I've already fucked this up when I wrote the answer key to the carbonyl assignment. I hit buttons too quickly and I didn't save, and so I had to write it out 3 times because I did it twice, and I saved after every single answer. And it's just weird because I've never lost them from a lecture, but watch today be the first day. So, okay, there we go. So let's say we have a different example. I want to make sure I get this right. I'm going to use another base that we're going to see. I'm going to start seeing it next class. It's called LDA. I'm going to draw it out. Lithium diisopropyl amide. Lithium, nitrogen, 2 isopropyl groups. Bulky base. Does not do nucleophiles. Let me rephrase that. Is not. Okay. Yeah, it is tricky. Okay, so I'm just going to draw this guy out bigger. Shit. Okay, and I'm going to draw it out bigger over here because I saved it, so it's a thing now. So I wasn't sure by inspection what the stereochemistry is at this center. I know there's a CH3 here, and it's fine to draw that in, but this is either out of the plane or into the plane once we make that new bond. And it's not clear to me whether it's in the plane or out of the plane. So you have a few options on how to do this. One thing you could do, which would be fine, is look and think, okay, the chlorine was coming out of the plane towards me. So the sulfur must be kind of going into the plane away from me. But now the problem is I've got both the hydrogen and the sulfur going into the plane away from me. So you need to be very careful about how you interpret that. You need to see it in 3D. I don't recommend you do this. It's really easy to fuck up. Because what I'm trying to figure out is what is the stereochemistry at carbon 1? So another way to do it is to draw what we've drawn here. So I rotate carbon 1 a little bit. So the chlorine is now in the plane. Carbon 2 is in the plane. I'm leaving carbon 2 frozen. The methyl group now comes out of the plane towards me when I rotate the chlorine. I smack it down, right? So I'm smacking the chlorine down. The methyl group comes out. The hydrogen kind of rotates from back into the left to back into the right. It's still back and away from the plane. Now when I'm making this new bond, I know the sulfur must come in directly opposite the chlorine. So it's pushing that. Now it's pushing against kind of like a triangle. So if I'm thinking about this, let's just draw carbon 1. We've got the methyl group. We've got the hydrogen. We've got the rest of the ring. I'm just going to draw it as a swirly thing. We have the S. We have the chloride. So we're forming that. So that came from S minus, and we're going to that. So we're kind of inverting the umbrella. The umbrella of the carbon, methyl, hydrogen was kind of open to the left. There's our umbrella was kind of inverted. And now our umbrella, this carbon, the hydrogen, and the methyl group is folded that way. So we have to invert the umbrella. If this does not make sense to you, ignore what I'm saying. If it makes sense and the other stuff makes sense to you, then that's fine. Whatever one of these things works for you, please use. That's really messy. So what I'm trying to do is line up the sulfur and the chloride and sort of show how the methyl and the hydrogen interact and what the stereochemistry is at those positions. So Victoria and Melitza, did that help at all? I'm really worried it didn't. I just couldn't tell. Yes, I think using a model kit would be great. I'm going to have a hard time showing it on the screen. I recommend you try it at home. I think if you haven't already, the textbook, this is where I think the ebook shines, is it's got a few animations of these SN2s occurring, and that might really help you see the motion of this thing and how this makes sense, and maybe that would really help. So I strongly recommend you try and take a look at that. I think I also put a few links to some resource. There might be some helpful links, resources, I think, that I copied over from last year. It's got a few of those videos as well. You can also type it into YouTube. There's actually a few good sort of illustrated with the animations versions of the Sn1 and Sn2, and I think those can be useful. I think it helps some people see the motion of this a lot. It's just you don't want me trying to animate it using like paper. Okay, so let's say we have this new example. So I'm telling you LDA is a base that is not a nucleophile. And we're going to see that needs to be stated because a lot of bases are nucleophiles and nucleophiles are bases. So if I'm telling you it's base, what would be the way to react this? Yeah, Sn2. What's our first step? Perfect. Thank you. So everyone's got this. I think some people are just able to skip a step, which is good for you. So it's negatively. I'm just going to think of it as negatively charged. It's the nitrogen of the aldehyde that's attacking. We move the electron, break the bond. We make our intermediate. Now what happens? I agree completely, Alyssa. I is a good leaving group. Where do we go with that? So O attacks I. Does it attack I? Attacks the carbon. I leaves and O minus attacks the carbon. Yeah, I like that better. And we agree it's an Sn2. So here's the question I've got, I guess. Does this do the reaction inter or intramolecularly? Yeah, it attacks the, yeah. So does it react within the molecule or with a different molecule? Or does it make a ring or not? Great, different molecule. Does not intermolecular. I know it's so confusing, inter and intra. It's a stupid name, isn't it? No ring. So it reacts with a different molecule. Note there's nothing stopping us polymerizing and start like just chaining these things together. We're only going to do 2 of them, but you could just keep this damn thing reacting. It would just because you have an electrophile and nucleophile in every molecule, And so they could just kind of attack each other and you can make a polymer. So we're attacking from the back side of the eye. So the oxygen, I'm drawing it in basically opposite, like anti-periplanar to it, like across from it. And that's going to push the eye out. And the fluorine and the hydrogen aren't going to, the fluorine's going to stay. It's just going to shift over from being up to the left to up to the right. This is awkward. And the iodine is going to stay on the bottom as well. So those will stay relative to it. Is fluorine also a good leaving group? Not as good as iodine. F- is actually a pretty shitty leaving group. It's like it's the exception to all the halogens. F-. Next course, those of you who are taking the class next term, you're going to do a lot of chemistry with F- as a leaving group. But in this course, F- is a shitty ass leaving group. Yeah, it just is. It's bad. Where'd you get them? There's a lot of them. There's a lot of these molecules. I got it from the starting material. We reacted with it. We got some product. There's an awful lot of them. There's just so much of this stuff floating around. Ooh, would it now make a ring? Well, 1, 2, 3, 4, 5, 6, 7, 8 carbon, 8 atoms. That's a bit long. I think we'd react with another molecule instead. And so we're going to kind of just, it'll react with another one. It'll start chaining itself along, making a polymer. But let's just do 1 for now. Yeah, 8 is a little bit too long. Now, if this had released something that was 6, absolutely it's going to make a ring, but it didn't give us 8, so yeah, didn't know. Okay, so when a ring, 5, 6. Look for acid-base reactions because they happen first, and often you need that to turn something into a good nucleophile. If we're looking for an Sn1 or an Sn2, we're under basic conditions here. Like if we break this whole thing down, we're basic Sn2. Our leaving group is primary, but fluorine can do resonance. So it's kind of like a resonance primary, but still we're under basic conditions. Polar aprotic solvent. We've got a lot going for us on the Sn2 side. How do we know? Because I basically told you that it's not a nucleophile. That's how we know. And Madison, that is not a dumb question. That's a really smart question because I changed that LDA a little bit. I don't use LDA for this. I use this guy, the dimethyl version. Suddenly, yeah, I think this is now, if you have enough of this, it'll deprotonate the alcohol and then it will start doing SN2s on that. Okay, I'm going to do one last example before we wrap up for today. Those of you who have to run, I understand. Those of you who have to run, I probably already run. It's a bit of a trick question. What does this do? Okay, Jesse says Sn1. Anyone else have an opinion? Yeah. So this is a tertiary leaving group. Sn2 is not possible. But I'm going to throw out that, well, methoxide can deprotonate methanol, but then you just get methoxide and methanol. So you're no further ahead. But basic conditions. Sn1, not possible. No substitution. It's going to be an elimination, and we're going to talk about eliminations starting next class. I think it's a good thing to go take a look at those videos if you've got the time. And we'll see how absolutely identical eliminations are to substitutions. That's lecture 17, I believe. So, or maybe 18. I seem to have 2 lecture 17s in my notes. I think eliminations are lecture 18. And so I think that's good because we're going to see that eliminations have an E1 and an E2 reaction. 23, whatever. I renumbered sorry, I guess I have old lectures that I have in front of me here. Lecture 23. Thank you. Eliminations and substitutions are in competition with each other. And so today what we focus on is what is Sn1 versus Sn2. Next class, we're going to start talking about the E1s and E2 mechanisms. And then we're going to enter the hell that is Sn1 versus Sn2 versus E1 versus E2, because they're all happening at the same time and are all in direct competition with one another. So if Samra is still here, I'm going to hand over to her. Don't see her, so maybe she's not here today. And if she's not, then that's okay. But I will let you guys take off. So have a good rest of your day. Ciao. Samurai is here. Yes, she'll take over. Hi. Do you need a stylus? I've got one actually. I brought a second one.
Yeah, I can break it. Thank you. I'll come grab it. Thank you.
Okay, where the hell did I put it? Come on in. Yeah. Damn it, I'm pretty sure I brought it in. There we go. I think it's charged. It's just seems to be running okay for me. It's not great. I might have another battery. Shouldn't be of this conversation. Quad A, yeah, sorry, the unique quad A. And I think I have some quad A's. I don't know where. The battery's not completely dead.
I have some at home.
Oh, okay, that's great.
Thanks. So, stills are done.
Are they great? Okay, awesome.
Finish it on Friday.
Okay. Congrats. Thank you. Okay, I'm gonna hand it over. She's walking back to the office now.
All right. Hi guys. Can you hear me? Olivia Drake Marie.